Welcome to this portfolio presentation about applied statistics by Jasper Ansems. First of all, the table of content. The first thing we're going to discuss is the case, which is made up by me. Then we're going to discuss distribution, process capability index, hypothesis testing, correlation and regression, and final forecasting. First of all, the case. A new restaurant has been opened in Eindhoven last year, 2016. The name of the restaurant is Fork, Knife and Glass. The owner of the restaurant is called Bart van Lokven. He is interested in statistics. For that reason, he wants to calculate multiple figures. With these figures, he can adjust his strategy and machines. Normal distribution. One of the meals in the restaurant is pizza. They use a machine to put the tomato sauce on the pizza. The machine puts 400 milliliters of sauce on the pizzas. The sauce delivered is distributed normally with the standard deviation of 10. What is the chance that a pizza has less than 385 milliliters of sauce on it? So the formula we're going to use is the value of C we need to find out, and that's individual observation minus the mean divided by the standard deviation. So the individual observation is 385, the mean is 400, divided by 10, which is the standard deviation, is minus 1.5. So we need to find this minus 1.5 in the table on the right. If we go down a bit, we find it that minus 1.5 is 0.00668. So from the table is 6.68%. So there is a 6.68% chance that a pizza has less than 385 milliliters on it. Binomial distribution. Every morning Bart decides the today's special. He makes his decision by throwing a dice. 1 and 2 is fish, 3 and 4 is meat, 5 and 6 is vegetarian. What is the probability that in 1 week of 6 days the fish is at most 2 times the today's special? So on the right is shown the formula and we need to fill in those numbers, but first we need to decide how are we going to calculate this. So at most 2 times means 2 or less. So by adding the chance of 0 times fish plus 1 times fish plus 2 times fish, we get 2 or less. So we need to fill in the formula. First of all, the first one is x is 0, then x is 1 and x is 2, as shown. So when we add these numbers up, we get a total of 0.681, and 0.681 is 61.1%, so there is a 61.1% chance that the fish is at most 2 times the today's special. The Poisson distribution. Per hour, the total number of reservations that are made is 2. What is the chance that exactly 3 reservations are being made in an hour? So this is the formula we're going to use, and we need to fill in those numbers from the little story we just read. So exactly through, so x is 3, and the number of reservations normally is 2, so we fill in that as well, and then we get the final number of 0.1804. We can also fill this in a table shown on the right. So we need to find those 2, and x is 3, and there they are. But because we only want exactly 3, we need to get the 0.8571 from the table, but minus the x is 2, because we only want the 3 and not the x or less, x2 or less. So the 0.8571 minus 0.6767 is exactly the same, is 18.04% that are 3 reservations being made in an hour. Next up is the process capability index. When a customer orders a drink or a soda at the restaurant, they want it delivered cold. For that reason, Bart uses an upper specification limit and a lower specification limit. The drink should be delivered between 15, which is the lowest specification limit, and 21 degrees, which is the upper specification limit, with a standard deviation of 1 and a mean of 18 degrees. So the simple formula we're going to use is USL upper specification limit min LSL lower specification limit divided by 6 times the standard deviation. 21 minus 15 divided by 6 times 1 is 1. So what does it actually mean? Well, when a CP is lower than 1, it's poor process. When it is 1, which we have right now, it's okay. And when it's bigger than 1, it gets good and excellent. But for this time, it's just okay. There's also another way of calculating the process capability. Bart has decided to buy a new refrigerator. With this refrigerator, the mean has gone up by 18.5 degrees. The USL and the LSL stay the same. So calculating this with the old formula is still 1 because we don't use the mean. But with the new formula CPK, we do use the mean because we take the USL minus the mean divided by 3 times sigma, and the mean divided by LSL divided by 3 times sigma, and we take the lowest result of that. So we fill that in with our own numbers, and that's equal to 1.5 divided by 3 or 4.5 divided by 3, but 1.5 divided by 3 0.4, which is the lowest. So here we see the differences between the two formulas. Statistical hypothesis, part 1. Testing whether a given hypothesis is likely to be true or not. One of the meals at fork, knife and glass is a big steak. Bart, the owner, wants a steak to be at least 500 grams. The weight of the steaks is distributed normally with a standard deviation of 50 grams. A test is done by weighing 100 steaks. The average weight of these steaks is 490 grams. Can we reject the claim from Bart based on this test? So to decide if we can reject it, we need to take a couple of steps. First of all, here's a small table of the results we can possibly get. And the first step is state the null hypothesis. So the null hypothesis is the steaks have an average weight of at least 500 grams. The mean is 500 or more. Step 2 is state the alternative hypothesis. The steaks have an average weight of less than 500 grams, so the mean is lower than 500. The next step is state the significance level, A, which is A is 0.05, and we need to look this up in a one tail, because we only want to know if it's lower. And then we find the value C, find the critical value, 1.64, as you can see on the right. Step 5 is calculate the test statistics. So first we have the formula, and then we're going to fill in the numbers. So the average of the test, X is 490, minus the mean is 500, divided by the standard deviation of 15, and we divide that standard deviation with the square root of n, and that was 100 because 100 steaks were tested. So 10 divided by 5 is 2. Step 6, reach a conclusion. The test statistics, Z is true, is greater than the critical value, 1.64. The null hypothesis is rejected. You can reject the claim from Bart based on the test. Pearson's correlation coefficient, R. Bart wants to know if there's a relationship between the age of the customer and the amount they spent that day at the restaurant. This can be done with Pearson's R. To measure how strong a relationship is between two quantitative variables. Here's the formula shown, but first we need a table. This is a result of the measurement. So we have 6 subjects, 6 people entered the restaurant that day, and we asked for their age, and that is shown in the table, and we wrote down the euros spent that day. So now we have a big table, and we're going to take this step by step. On the left, subject age and euros spent was already shown on the previous sheet, and we added them up. H is added up 312 euros are added up is 276. So the average of 312 is 52, and the average of that 276 is 46. So the first step, we're going to go one column right, and we see x minus the average of x. So for instance, for this first subject, h minus average, h minus 52, so 35 minus 52 is minus 17, and we did that for all the rows. We did the same for y, so one column to the right is for subject 1, 44 euros spent, minus the average is 46, is minus 2. Then one column to the right, we take that minus 17 from the first subject times that minus 2 from the first subject, which is 34. And we added all those numbers up from the x times y, and we come to 994. Then we're going to go to the next column, which is that x minus the average of x to the power of 2. So minus 17 to the power of 2 is 289. And we did that for the entire column. We also did that for y. So for the first subject, minus 2 to the power of 2 is 4. And we added those up as shown in the table. To find out the standard deviation of h and euros spent, we take that total of 2,375 from the x minus the average of x to the power of 2, and we divide it by the subjects, which is 6. Then we get 395.8, and the square root of that is 19.9. We also did that for y. 546 divided by 6 is 91. The square root of 91 is 9.5. So now we go back to the formula again. Is shown below the table. So first of all, we're going to take that x minus the average of x times y minus the average of y is 994, and we're going to divide that by the number of subjects, which is 6, times the standard deviation of h times the standard deviation of euros spent is 0.8763, which means there's a fairly big relationship between the h and the euros spent. So when the h go up, almost every time the euros always will go up. Spearman's rank correlation coefficient. This measures the strength of association between two ranked variables. Bart has 10 people serving food and drinks. Bart wants to know if there's a relationship between the employees who sell more drinks and the employees who sell more food. He decides to measure the amount of purchases for one day, which is shown in this table. So for instance, for employee 1, he or she sold 38 drinks and he or she sold 35 times food. In this table, the first three columns are the same, so employee, drinks and food is the same. The next column we ranked the D, so drinks. So for employee 6, he sold 60 drinks, which means he is number 1. And for employee 4, he sold 31 drinks, which means he's number 10 in rank. We also did that for food. So employee 9 sold 51 times food, so he gets rank 1. And employee 4 again sold 34 times food, which means he gets rank 10. Then we divide D minus F rank. So D rank for employee 1 is 8, F rank for employee 1 is 9, so 8 minus 9 is minus 1. We did that for the entire column, and then we put those numbers to the power of 2. So for employee 1, D rank minus F rank is minus 1, to the power of 2 is 1. All those numbers were added up and we came to 38. So now we can fill out the formula. So 1 is 6, which is all the time 6, and then the sum of D rank min f rank to the power of 2 is 38, divided by 10 employees, and then 10 to the power of 2 is 100 minus 1 is 0.7697, which means there's a very big relationship between the drinks and the food sold. Regression. Last week Bart started advertising. He wants an overview where there's a comparison being made between the amount spent on advertising and the income over that period. So on the first day he spent 10 euros on advertising, and on the last day, Saturday, he spent 60. And also we wrote down the income for that day. So the formulas we're going to use is this one, where we can find the regression line, but in this formula we also need, first we also need to calculate A and B. So B is calculated like this, and A is calculated like this. So we take the same first three columns of the previous slides, but we do some calculations. So on the fourth column we take x to the power of 2. So for the first row, 10 to the power of 2 is 100. And in the last column we take x times y. So 10 times 252 is 2520. We add those numbers up and we get a total and a mean for x and y. So now we can fill out B. This is the formula of B. So n is 6 days, times that 69,720, which is the total, minus 210, which is the total of x, times the total of y, divided by, again, 6 times 99,100 minus the average of x to the power of 2 is 2.4086. And now we need to calculate A. So A is shown here, the formula. So the average of y was 312.2 minus B, which we just calculated, times the average of x is 35, is 227.87. So we can say, thus the best fitting line is 278.87 plus 2.4086 times x. And we also calculated this in Excel, which is shown here, and we see that the formula shown in the Excel graph is exactly the same as we just calculated. Forecasting. Over the last year, Bart documented the sales of every project. One of these projects was a salad. Bart documented the purchases of this salad for each season. The first season, spring, he sold 200 salads, summer 600, fall 300 and a winter 100. It comes to a total of 1200 salads sold. So the average sold salads per period was 300. But we need to calculate the percentages. So in spring there were 200 salads sold, divided by the mean is 300 is 67%. And we also did that for the summer, it's 200%, for the fall is 100%, for the winter it's 33%. Bart suspects that for upcoming year the demand for the salads will be 1600. So the seasonalized demand per period is 400, because 600 divided by 4 is 400. So we're going to take those percentages we just calculated and we put them in this calculation. So 400 times 67% is 268. For summer it's 800, for fall it's 400, and for winter it's 132. Add those numbers up and we get the same 1600. Moving average. Every first Monday of the month, Bart orders his raw goods. For the salad he needs tomatoes. He wants to know how many tomatoes he needs for the upcoming months. So the moving average formula is shown on the left, but first we need a table, which is shown here. So we have 12 months, and on the actual column we see how many tomatoes he actually needed, and then we need to do some calculations. So we take the first 3 months of the year, 48, 50 and 53, we put them together and we get 151, and we divide them by the total months we just added up, is 50, Well, actually 50.3, but because it's whole tomatoes, we can't order 1/3 of a tomato, so 50. And we also did that for a moving average of 6 months. When we add the first 6 months and we get 299 divided by 6 is also 50. We also have exponential smoothing. Barts want to calculate the need of tomatoes in another way by using the same numbers but with a new formula. So this formula is new forecast is A, which Bart can decide for himself, times the latest demand plus 1 minus A times previous forecast. So we have the same table as last sheet, and now we need to decide for May, June and July our forecast. Bart decides to put 80% weight on the old forecast and 20% weight on the last month. So the forecast for May is A is 1.8 times 47, which is the latest demand in April, plus 1 minus that 80% times 50, and that 50 is the latest forecast, the previous forecast, which comes to 47. And we need that 47 for calculating June, because in June we take the same 0.8 times the 54, which is the demand in May, plus 1 minus that 80% times the 47 we just calculated. And when we fill in those numbers, we get a table like this. This is the end of the presentation. Bart van Lokven is now a happy man because with statistics he knows a lot more about his company.